The proliferation of AI agents often led to a critical dilemma. How could these agents offer rich, interactive experiences beyond simple text, without compromising security or consistency? Traditional chat interfaces, while intuitive for simple queries, struggled with the complexity of multi-step tasks and dynamic data presentation. This limitation hindered their utility in complex enterprise environments. Conventional chat-based AI interfaces present significant limitations. They often lack the ability to adapt responses based on individual user data, roles, or past interactions, leading to repetitive and inefficient exchanges. Users frequently struggle to articulate complex needs precisely in text, resembling the cognitive burden of command-line interfaces. This reliance on text also means a lack of immediate visual feedback, slowing down trial-and-error processes and making complex tasks cumbersome. Furthermore, discoverability of AI capabilities becomes difficult, as users must infer functionality rather than seeing it explicitly presented. Google introduced MCP Apps to address these limitations, bringing interactive AI applications directly into conversational interfaces. Instead of confining AI output to mere text or markdown, MCP Apps allow agents to invoke and display rich, dynamic web-based user interfaces. This shift provides agents with a visual voice, enabling them to present complex information, forms, or interactive tools directly within the chat environment. It facilitates a more intuitive and efficient user experience by moving beyond static responses to fully interactive applications. MCP Apps function by treating UI as a resource. When an AI agent needs to display an interactive element, it issues a tool call, and an MCP server responds with the HTML and JavaScript assets of a pre-built web application. This application is then rendered within a sandboxed frame inside the user's host application. The configuration and interaction with this UI occur through the existing Model Context Protocol, allowing the agent to control the application's content and appearance effectively. The architecture of MCP Apps centers on this sandboxed frame approach. The MCP server delivers the application's HTML and JavaScript, which the agent embeds within a structured A2UI JSON payload. This consolidated JSON is dispatched to the host, rendering the MCP app inside an iframe wrapper, alongside other A2UI native components. This design provides a secure and flexible way to integrate custom web applications into diverse agentic environments, abstracting away much of the underlying complexity for developers. The MCP Apps lifecycle involves several stages. It begins with a tool call initiated by the agent to access specific functionality. This triggers the delivery of an HTML app bundle from an MCP server. This application then runs within a sandboxed runtime, an isolated frame in the host interface, protecting against security risks. User interaction within this app generates agent feedback, which is then sent back to the agent, creating a continuous feedback loop that drives dynamic responses and actions. Sandboxed HTML applications are a core security feature of MCP Apps. They isolate developer-written web code within an iframe, enforced with content security policies and strict permissions. This isolation prevents arbitrary runtime code execution from an agent, mitigating security risks. A double iframe isolation pattern is often employed, using an intermediate iframe to further isolate raw DOM injection from the main application, while maintaining a structured JSON RPC channel for communication. Agentic user interfaces represent a paradigm shift where AI orchestrates the user experience. Instead of static, hard-coded interfaces, agentic UIs adapt dynamically based on user intent and context, enabling agents to build, modify, and improve interface layouts in real time. This allows AI to translate complex reasoning into a complete, functional, and interactive experience, moving beyond mere text output. Agentic UIs are crucial for tasks requiring multi-step planning and interaction with external tools. Generative UI is a front-end architecture where the user interface is created in real time by AI, rather than being hard-coded by developers. Large language models orchestrate the UI, adapting layout, components, and data visualization based on specific user intent and session context. This approach aims to provide a personalized, dynamic interface that shifts to suit each individual user, drastically speeding up development cycles and improving user experience. A2UI, or Agent-to-User Interface, is an open-source UI toolkit designed by Google for native generative user interfaces across various platforms. It facilitates LLM-generated UIs across trust boundaries using a secure, declarative JSON line stream to send UI structures and data models from agents to client applications. Because A2UI transmits declarative data rather than executable code, it is inherently secure and framework-agnostic, allowing agents to speak UI natively on web, Flutter, Android, and iOS. Google introduced A2UI to standardize how AI agents exchange user interfaces, not just text, across diverse platforms and applications. The goal was to address challenges of interoperable, cross-platform, generative, or template-based UI responses from agents. It ensures that agents can generate contextually relevant interfaces that render natively, providing a high-quality user experience regardless of the front-end application. A2UI mitigates security risks by transmitting declarative data, not executable code. A2UI and MCP apps address agent-generated UI with distinct strengths. MCP apps are ideal for web-first applications, offering maximum UI flexibility and rapid prototyping within sandboxed iframes, giving the server full control of the UI experience. In contrast, A2UI prioritizes native applications, security-critical use cases, and cross-platform consistency, with agents sending declarative component blueprints that the host application renders using its own styling and components. A2UI is best when standard host native components can carry the workflow. A2UI and MCP apps are complementary and can be combined to leverage their respective strengths. One pattern involves an MCP app bundle containing its own A2UI renderer, fetching dynamic A2UI interfaces through a tool call to retrieve the A2UI payload. Another approach allows serving A2UI over MCP servers, where an MCP tool can return A2UI payloads alongside HTML resources. This unified architecture provides both creative expressiveness and secure, native-feeling UIs. Interactive state synchronization between agents and UIs is critical for maintaining consistency in complex workflows. The A2UI rendering engine, for example, maintains state across both native components and embedded MCP apps using a secure, event-driven cycle. This ensures that as users interact with the UI, their actions are relayed back to the agent, updating the underlying data model, and subsequently, the UI reflects the current agent and user state, preventing divergence between the UI, the model, and the backend. Gemini serves as a powerful AI interface runtime, enabling models to orchestrate and generate complex user experiences. For instance, the Gemini app integrates generative UI capabilities, allowing it to design and code fully customized interactive responses for each prompt. This extends to Google Search's AI mode, where Gemini 3's multimodal understanding and agentic coding capabilities instantly build bespoke generative UIs, creating dynamic environments optimized for deep comprehension and task completion. Google AI Studio offers integration with MCP, allowing developers to build, deploy, and scale AI apps faster. This integration enables MCP-compatible AI agents to deploy applications to Cloud Run via a new Cloud Run MCP server. Furthermore, a Model Context Protocol server integrated with Google AI Studio and Gemini API provides content generation capabilities with support for files, conversation history, and system prompts, enhancing the development flexibility for AI-powered applications. Tool discovery and agent registry are essential for agents to leverage external capabilities efficiently. The Model Context Protocol standardizes how AI agents find and interact with external systems, content repositories, business tools, and development environments. This allows AI products to discover available tools, read structured resources, receive prompts, and call functions on external systems. Google's initiatives, including the Agent Development Kit, facilitate building multi-agent systems with orchestration and memory, natively supporting A2UI. Enterprise use cases for Google MCP apps and A2UI are extensive, encompassing critical business functions. For Workspace, agents can generate dynamic dashboards or interactive forms for data entry. BigQuery and Cloud SQL benefit from agents that can visualize complex query results or create data exploration interfaces. Google Maps leverages the Maps Agentic UI toolkit to turn AI text into interactive maps, providing rich visual context for geospatial queries, routes, and place details within conversational experiences. Cross-platform compatibility is a key design principle, enabling agentic interfaces to extend beyond Google's ecosystem. A2 UI, for example, is framework agnostic, supporting native rendering on Angular, Flutter, React, and other environments. MCP apps are also designed for use with other MCP hosts like Claude and ChatGPT, and the Agent User Interaction Protocol facilitates communication with front-end frameworks like those used in VS Code. WebMCP extends agentic interfaces to the web by allowing websites to expose structured capabilities directly to AI agents. Instead of agents relying on fragile DOM scraping or simulating clicks, WebMCP lets developers explicitly define actions as JavaScript functions with natural language descriptions and structured schemas. This transforms web pages into deterministic, machine-readable interfaces, enabling more reliable and efficient agent interaction directly within the browser. MCP apps and WebMCP address different interaction paradigms. MCP apps create new, separate applications rendered within an agent's UI, often in sandboxed iframes, giving the app owner full control over the UI. Conversely, WebMCP enables agents to interact with websites in real time, accessing live session data and DOM elements. WebMCP is browser-side and ephemeral, existing only when the page is open, while MCP is server-side, connecting agents to back-end data and services. The agent protocol stack encompasses several critical components. At its base is the Model Context Protocol, standardizing how AI agents interact with their environment. Building on this are MCP apps, offering sandboxed interactive web applications. A2 UI provides native generative user interfaces, while A2A, the agent-to-agent protocol, enables agents to collaborate. AGUI facilitates agent-user interaction, and WebMCP extends agentic interfaces directly to the web. Current adoption of these protocols is growing, with significant development and integration. A2 UI, now at version 0.9, is openly available and seeing implementations across various rendering frameworks. MCP apps are being adopted by major AI platforms, and WebMCP is in early preview, with Chrome supporting it behind flags. Google AI Studio integrates MCP, and enterprise solutions leveraging these protocols, like the Maps Agentic UI toolkit, are in experimental stages. Current limitations exist within this evolving landscape. While A2 UI ensures security by using declarative data, its flexibility is constrained by the host's existing component library. MCP apps, while offering flexibility, introduce complexities with cross-origin security boundaries and potential performance overhead from iframes. WebMCP, though promising, is still experimental, lacks native browser support, and requires a browsing context, limiting headless operations. State divergence between the UI, model, and backend also remains a critical engineering challenge. The future of agentic user experiences points towards increasingly seamless and intelligent interactions. Agents will move beyond simple chat, anticipating user needs and proactively surfacing information or actions through subtle notifications or widgets. This will involve a deeper integration of AI into everyday applications, where interfaces dynamically adapt to user intent, providing highly personalized and efficient workflows that minimize cognitive load and maximize productivity. The future of AI interfaces is characterized by dynamic, context-aware, and multimodal interactions. Instead of users adapting to fixed interfaces, the interface will adapt to them, with AI generating and refining UI elements in real time. This will lead to a richer, more visually intuitive experience across web, mobile, and desktop, where AI agents act as intelligent orchestrators, turning abstract prompts into functional, interactive applications that enhance human creativity and productivity.